Black holes have long captivated the imagination of scientists and the public alike, standing as some of the most mysterious and intriguing objects in the universe. Their immense gravitational pull is so powerful that not even light can escape. Once it crosses a certain boundary, known as the event horizon, this baffling characteristic has made black holes not just astronomical phenomena, but profound puzzles that challenge our understanding of physics and the cosmos. The question at the heart of much contemporary discussion is simple yet profound. Could black holes be gateways to other universes? This idea stretches beyond the conventional boundaries of astrophysics, venturing into the realms of cosmology, quantum theory, and even philosophy. The historical journey toward understanding black holes began over a century ago, rooted in Einstein's theory of general relativity, which predicted the possibility of these dense, invisible objects. Early skepticism gradually gave way to acceptance as observational evidence accumulated, notably through discoveries such as quasars and the detection of X-ray emissions from black hole candidates. Over time, black holes evolved from theoretical curiosities to essential components in explaining the structure and evolution of galaxies, including our own Milky Way. Today, the enigmatic nature of black holes continues to fuel debates and inspire new theories. The notion that they might serve as portals or gateways to other universes taps into speculative but scientifically grounded ideas such as wormholes and the multiverse. While these concepts remain unproven, they offer tantalizing possibilities that challenge and expand the horizons of modern physics. This exploration into whether black holes could be gateways to other universes invites us to reconsider not just what we know about the cosmos, but the very nature of reality itself. The origins of black hole theory trace back much earlier than the 20th century, surprisingly rooted in ideas that predate Einstein's revolutionary work by over a century. In the late 18th century, the notion of a dark star was first proposed by John Michell, an English natural philosopher and geologist. Mitchell was intrigued by the idea that gravity, which holds planets in orbit and causes objects to fall toward Earth, could also be powerful enough to prevent even light from escaping a massive celestial body. This concept, remarkable for its time, suggested that such objects could exist in space, massive enough to trap light within their gravitational grasp and yet be invisible to observers, because no light could escape to reach them simultaneously. The French mathematician and astronomer Pierre-Simon Laplace, working independently, articulated a similar hypothesis. In his early 1790s writings, Laplace proposed that some stars could have such strong gravity that light itself would not be able to escape their surface. These dark stars, as they were sometimes called, existed only as theoretical possibilities. Within the bounds of Newtonian physics and the wave theory of light, which had yet to be fully understood, both Mitchell and Laplace's ideas, though innovative, were speculative and largely overlooked by their contemporaries, largely because the nature of light and gravity's influence on it was not fully grasped at that time. The scientific community in the 18th and 19th centuries remained skeptical about these dark stars because Newtonian mechanics could not fully explain light's behavior under gravity, and because no observational evidence existed to support the presence of such objects. For most scientists of the era, light was thought to be massless particles traveling at a constant speed unaffected by gravity, which would make the idea of a gravitational trap for light seem impossible. Progress in the understanding of light's nature during the 19th century, including the wave theory and later the discovery of electromagnetic waves by James Clerk Maxwell, set the stage for a radical shift in thinking about gravity and light interactions. However, the true breakthrough came with the dawn of the 20th century and Albert Einstein's formulation of the general theory of relativity in 1915, which fundamentally altered our understanding of gravity. Einstein proposed that gravity was not a force acting at a distance, as Newton had described, but rather a curvature of space-time caused by the presence of mass and energy. According to this theory, massive objects cause the fabric of space-time itself to curve, and this curvature directs the motion of objects and light. This framework allowed for the theoretical possibility that space-time could be warped to such an extreme degree that a region could form where the escape velocity exceeded the speed of light. This region would essentially trap everything, including light, making it invisible from the outside, precisely the characteristics earlier envisioned by Mitchell and Laplace. Shortly after Einstein published his equations, the German physicist Karl Schwarzschild found a precise solution to these field equations, which described the space-time geometry surrounding a spherical, non-rotating mass. Schwarzschild's solution mathematically predicted what we now recognize as a black hole, although the term itself had not yet been coined. His work revealed a critical radius, later called the Schwarzschild radius, which marks the boundary now known as the event horizon, beyond which nothing could escape the gravitational pull of the mass enclosed. Despite this elegant mathematical description, the physical reality of such objects was met with skepticism. Many physicists viewed black holes as mere theoretical oddities, perhaps mathematical singularities that arose due to the idealized assumptions of the model, but not something that could truly exist in nature. The concept of a singularity, a point where density becomes infinite and known physical laws break down, was particularly troubling and unsettling. Through the mid-20th century, black holes remained on the fringe of mainstream astrophysics. A lack of direct observational evidence, combined with conceptual difficulties in understanding what a black hole really was, meant that the topic was often considered speculative or even metaphysical, rather than a serious subject of scientific inquiry. Some scientists tried to interpret these solutions as theoretical tools useful in calculations, but doubted whether nature actually produced such extreme objects. However, the tide began to shift as more astrophysical phenomena were discovered that could not be explained by classical physics. The identification of quasars extremely bright and distant celestial sources emitting enormous amounts of energies suggested the presence of extremely compact and massive objects capable of powering such energetic emissions. This, along with the discovery of X-ray sources in binary star systems in the 1960s, provided indirect but compelling evidence for the existence of black holes as physical entities. The theoretical framework also advanced with the work of physicists like John Wheeler, who popularized the term black hole in the late 1960s. Wheeler helped bring the concept out of the shadows of obscurity and into mainstream physics, emphasizing black holes as a natural consequence of Einstein's general relativity rather than mere mathematical curiosities. This was complemented by work on black hole thermodynamics and the discovery of phenomena such as Hawking radiation in the 1970s, which showed that black holes could emit radiation due to quantum effects near the event horizon, further solidifying their status as physical objects subject to the laws of physics. Thus, the journey from the early dark star hypotheses to the acceptance of black holes as genuine astrophysical objects reflects a remarkable transformation in scientific understanding. It was a gradual process shaped by advances in theory, observations, and technological capabilities. What started as philosophical speculation evolved into one of the most active and exciting fields of modern astrophysics. Throughout this evolution, the essential mystery of black holes, these regions where our conventional understanding of space, time, and matter breaks down, remained intact. It is this very mystery that leads contemporary scientists to ask even more profound questions, such as whether black holes might serve as gateways to other universes, pushing the boundaries of cosmology and theoretical physics, building upon the initial theoretical acceptance. The mid-20th century witnessed an intensification of efforts to understand black holes, not just as static solutions, but as dynamic, physical entities influencing and shaping the cosmos. One pivotal figure in this development was Roger Penrose, whose work in the 1960s introduced rigorous mathematical theorems about the inevitability of singularities forming under certain gravitational collapse conditions. Penrose demonstrated that if a massive star exhausted its nuclear fuel and underwent gravitational collapse, it would form a singularity hidden within an event horizon, a black hole as a real astrophysical object rather than an abstract mathematical construction. Penrose's work helped dispel lingering doubts by establishing that black holes could naturally form in the universe through well-understood stellar processes. This bridged the gap between the abstract mathematics of general relativity and the physical reality of star death and cosmic phenomena. It also contributed to the understanding that black holes are not isolated curiosities, but key players in the life cycles of stars and galaxies. Simultaneously, advancements in observational astronomy started providing indirect evidence to back up these theoretical predictions. The development of radio and X-ray astronomy opened new windows into the cosmos. Astronomers discovered powerful sources of radio waves and high-energy radiation, emanating from regions too small and too energetic to be explained by normal stars or gas clouds. These observations hinted strongly at compact objects with gravitational fields strong enough to accrete matter and emit enormous radiation, consistent with the predicted behavior of black holes. A particularly famous case was Cygnus X11, of the first strong black hole candidates identified in the early 1970s. This binary system includes a visible star orbiting an unseen companion emitting X-rays. Detailed measurements showed that the companion's mass exceeded the limit of neutron stars, leaving a black hole as the only viable explanation. This discovery marked a watershed moment, transforming black holes from theoretical predictions into observable astrophysical entities with measurable properties. Further breakthroughs came from the study of supermassive black holes believed to reside at the centers of galaxies, including our Milky Way. Observations of stellar orbits near the center of the Milky Way revealed the presence of an extremely massive yet compact object, consistent with a supermassive black hole millions of times the mass of our Sun. These findings underscored black holes' central role in galactic evolution, shaping star formation, gas dynamics, and the overall structure of galaxies. The acceptance of black holes as genuine cosmic phenomena also stimulated new theoretical explorations. Physicists began investigating the intricate structure of space-time around black holes, leading to the concept of the event horizon as a one-way boundary beyond which information cannot escape. This raised deep puzzles about the fate of matter and information inside black holes, famously encapsulated in the information paradox. Such paradoxes highlighted the need to reconcile general relativity with quantum mechanics, spurring the search for a theory of quantum gravity in parallel. Theoretical models proposed exotic possibilities, such as wormholes, hypothetical tunnels through spacetime that might connect distant points or even separate universes, while wormholes remain speculative and unobserved. Their theoretical feasibility within Einstein's framework invited scientists to ponder whether black holes could be portals, not just within our universe, but between universes in a broader multiverse landscape. Throughout this rich history, the gradual progression from early speculation about dark stars to the modern understanding of black holes as dynamic, influential cosmic entities reflects a profound evolution in scientific thought. Each discovery and theoretical advance has deepened the mystery, revealing black holes as not only the endpoints of massive stars, but as potential keys to unlocking the greater structure of reality itself. The intricate structure of a black hole is as fascinating as its origin story, revealing an extraordinary complexity hidden behind the veil of invisibility. To comprehend how black holes might function, especially in theories suggesting they could act as gateways to other universes, it is essential first to understand the fundamental anatomy of these cosmic phenomena. Central to this understanding are concepts such as the event horizon, the singularity, and, in certain types of black holes, the ergosphere. These features collectively shape the black hole's interaction with space-time and dictate how matter and energy behave in its extreme environment. The event horizon is perhaps the most defining boundary of a black hole. It marks the point of no return, a spherical surface enveloping the black hole from which nothing, not even light, can escape the gravitational pull. According to classical general relativity, once an object crosses the event horizon, it is irrevocably drawn inward, toward the black hole's core. The event horizon thus serves as the black hole's invisible surface. Although it is not a physical surface, like that of a planet or star, but a mathematical boundary in spacetime. The radius of the event horizon, known as the Schwarzschild radius for non-rotating black holes, depends solely on the black hole's mass. For example, a black hole with the mass of our Sun would have a Schwarzschild radius of about 3 kilometers, whereas a supermassive black hole, millions or billions of times the Sun's mass, would have an event horizon spanning millions of kilometers. This scale directly influences how the black hole warps the surrounding space-time, producing effects that can be observed indirectly by studying the behavior of nearby stars, gas, and light. Inside the event horizon lies the singularity, the central point where all the mass of the black hole is thought to be compressed into infinite density and zero volume. This concept, however, challenges the very foundations of physics, as classical general relativity predicts the singularity as a point where space-time curvature becomes infinite. Unknown laws of physics cease to function. The singularity is hidden from outside observers by the event horizon, safeguarding cosmic censorship by preventing the breakdown of physical laws from being visible in the wider universe. Despite its theoretical nature, the singularity represents the ultimate mystery of black holes. It symbolizes a boundary not just in space, but in our understanding of reality. Physicists have long sought to resolve the paradoxes posed by singularities through attempts to develop a quantum theory of gravity, which would unify the macroscopic predictions of general relativity with the microscopic laws of quantum mechanics. Until such a theory is achieved, the singularity remains an enigmatic core shrouded in mystery for rotating black holes, known as Kerr black holes, after mathematician Roy Kerr, who found their solutions in 1963. the anatomy becomes even more complex. These black holes possess an additional feature called the ergosphere, an oblate region outside the event horizon where space-time is dragged around by the black hole's rotation. This effect, called frame dragging, twists the fabric of space-time itself, forcing objects in the ergosphere to co-rotate with the black hole. The ergosphere is significant because it provides a region where energy can, in principle, be extracted from a rotating black hole, a phenomenon predicted by physicist Roger Penrose, and now known as the Penrose process. This idea has far-reaching implications for understanding black hole dynamics and the potential mechanisms by which black holes interact with their surroundings, possibly influencing the formation of powerful jets observed in active galactic nuclei. The shape of the ergosphere differs from the event horizon. It is flattened at the poles and bulges out at the equator, creating a dynamic boundary region where exotic effects dominate. Unlike the event horizon, objects can theoretically enter and leave the ergosphere, making it a realm of intense energetic interactions and a key focus in studying how black holes may serve as cosmic engines. Further out from the event horizon and ergosphere lies the accretion disk, a swirling mass of gas, dust, and stellar debris spiraling into the black hole. Though technically outside the black hole itself, the accretion disk is vital for understanding observational signatures and energy emissions. As matter in the disk accelerates and heats up due to friction and gravitational forces, it emits X and other radiation detectable by astronomers, providing indirect evidence of black holes. The intense gravitational gradients near the event horizon cause phenomena such as gravitational time dilation, where time appears to slow dramatically for an object approaching the black hole compared to a distant observer. This effect arises directly from the extreme curvature of space-time and has been confirmed through experiments and observations consistent with Einstein's predictions. Importantly, the interplay between the event horizon, singularity, ergosphere, and the surrounding space-time geometry lays the groundwork for advanced theoretical models. Some of these models explore whether the black hole's internal structure could connect to other regions of space-time, potentially forming bridges or tunnels, wormholes, that might link to distant points in our universe, or even entirely separate universes. Such ideas, while speculative, are rooted in the mathematical flexibility of general relativity and have motivated physicists to examine the black hole interior beyond classical descriptions. Moreover, the behavior of matter and information near these boundaries raises profound questions. The black hole information paradox, for example, challenges the assumption that information is never lost, conflicting with quantum theory principles. Resolving this paradox is crucial for understanding the fundamental nature of black holes and their role in the broader universe. In sum, the anatomy of a black hole lit event horizon defining the ultimate boundary, the mysterious singularity at its core, and the dynamic ergosphere in rotating cases, forms a complex interplay shaping how these objects interact with the fabric of space-time. This detailed understanding not only clarifies the mechanics of black holes, but also sets the stage for contemplating their potential role as gateways or conduits to realms beyond our current perception. To further explore the anatomy of black holes, it is crucial to delve deeper into how the event horizon functions not only as a spatial boundary, but as a dynamic interface that governs. To further explore the anatomy of black holes, it is crucial to delve deeper into how the event horizon functions not only as a spatial boundary, but as a dynamic interface that governs the flow of information and energy. While classically, the Event horizon is a one-way membrane. Recent theoretical insights have suggested a more nuanced picture. The event horizon behaves like a kind of thermal surface, with properties described by black hole thermodynamics. This analogy emerged from the groundbreaking work of Jacob Bekenstein and Stephen Hawking in the 1970s, who showed that black holes possess entropy proportional to the area of their event horizon, and can emit radiation now known as Hawking radiation due to quantum effects near this boundary. This discovery profoundly altered our understanding of black holes, implying they are not entirely black or eternal, but can slowly lose mass and eventually evaporate over extraordinarily long time. Hawking radiation also introduced the puzzling question of what happens to the information encoded in matter that falls into a black hole, further intertwining quantum mechanics with black hole physics and deepening the mystery surrounding their interiors. The singularity, traditionally viewed as a point of infinite density and breakdown of physical law, might be more complex when considering quantum gravity effects. Some modern approaches, such as loop quantum gravity and string theory, suggest that the singularity could be replaced by a finite, albeit extremely dense, region where new physics emerges. These theories propose mechanisms by which the classical notion of a singularity is softened, potentially avoiding infinite quantities and allowing a consistent description of the black hole interior. Another fascinating aspect of black hole anatomy is the concept of the Cauchy horizon in rotating and charged black holes, such as the Kerr and Reisner-Nordstrom solutions. The Cauchy horizon is an inner horizon beyond the event horizon, behind which the deterministic nature of space-time breaks down. In these scenarios, the structure inside the black hole becomes more intricate, featuring layers of horizons and complex causal properties. Some theoretical models suggest that the region inside might be connected to other universes or distant parts of our own universe. Though these ideas remain speculative and subject to intense debate, the ergosphere, specific to rotating black holes, also plays a critical role in possible energy extraction mechanisms. The Penrose process, for example, allows particles entering the ergosphere to split, with one falling into the black hole and the other escaping with more energy than the original. This theoretical process has implications for astrophysical JETS streams of high-energy particles, observed emanating from active galactic nuclei and quasars, and offers insight into how black holes can influence their environments far beyond their event horizons. Together, these anatomical features reveal black holes as far more than simple gravitational traps. They are dynamic, complex systems interacting with space-time, matter, and energy in ways that challenge and expand current physics. Understanding this anatomy not only aids in grasping their nature, but also provides the conceptual foundation for exploring the tantalizing possibility that black holes could be gateways, perhaps wormholes connecting different parts of the cosmos or even different universes altogether. This foundation is crucial because the possibility of black holes serving as cosmic portals depends heavily on the structure and behavior of their event horizons, interiors, and surrounding spacetime. The theoretical models built on this anatomy form the basis for much of the speculative, yet scientifically informed, research into multiverse scenarios and higher dimensional spaces. The concept of wormholes introduces a fascinating possibility that goes beyond the traditional understanding of black holes as mere cosmic traps. Wormholes, sometimes called Einstein-Rosen bridges, after the physicists who first proposed them, are theoretical passages through space-time that could connect two distant points within our universe, or even link entirely separate universes. This notion elevates black holes from endpoints of matter and information to potential gateways, a hypothesis that has captured the imagination of both physicists and the public. The idea of wormholes emerged directly from Albert Einstein's theory of general relativity, which describes gravity as the curvature of space-time caused by mass and energy. In 1935, Einstein, together with his colleague Nathan Rosen, explored solutions to Einstein's equations that described what we now call the Einstein-Rosen bridge. Their work suggested the possibility of a bridge connecting to separate regions of space-time, effectively creating a tunnel-like structure through the fabric of the cosmos. This theoretical construct was initially a mathematical curiosity, revealing the extraordinary flexibility of general relativity and the potential for space-time to have non-trivial topologis. An Einstein-Rosen bridge, in its original form, connected to black holes, or more precisely, to Schwarzschild solutions, by a hypothetical throat. However, it was quickly understood that these bridges were unstable and would collapse too quickly for anything to pass through. This instability meant that practical travel through such a wormhole, if it existed at all, would be impossible under normal conditions. Nonetheless, the very idea that space-time could be connected by such shortcuts inspired further theoretical investigation. In the decades following the Einstein-Rosen paper, physicists refined the concept of wormholes, exploring whether such structures could be stable and traversable. The concept of a traversable wormhole, one through which matter could safely pass, was advanced by theoretical physicists such as Kip Thorne and Michael Morris in the 1980s. They demonstrated that, under certain conditions, it might be possible to keep a wormhole's throat open using exotic matter, hypothetical material with negative energy density that defies normal physical properties. This exotic matter would exert a repulsive gravitational effect, counteracting the natural tendency of the wormhole throat to pinch off and collapse. While no such matter has been observed in nature, the theoretical possibility opened doors to imagining wormholes not just as abstract concepts, but as potentially real features of the universe. With profound implications for physics and cosmology, the idea that black holes might be connected to wormholes has been a recurring theme in this research. Some speculative models propose that the interior of certain black holes could harbor a wormhole structure, linking to other regions of space-time or alternate universes. In these models, matter falling into a black hole might not be destroyed at a singularity, but instead pass through a wormhole to emerge elsewhere, potentially circumventing the classical singularity problem. Wormholes also present intriguing possibilities related to time travel. Because of their unique structure, some solutions to Einstein's equations suggest that wormholes could connect not only different locations in space, but different points in time. This introduces the tantalizing, yet paradoxical, idea of temporal loops and causality violations, which challenge fundamental assumptions about the nature of cause and effect. Despite the allure of these ideas, wormholes remain speculative and largely theoretical. The conditions required for their existence, such as the presence of exotic matter and the challenges related to their stability and formation, are significant barriers to considering them physically realistic with current scientific knowledge. Nonetheless, they provide a valuable conceptual framework for understanding the potential extremes of space-time geometry allowed by Einstein's theory. The exploration of wormholes has also intersected with developments in quantum gravity and string theory. These advanced frameworks seek to unify general relativity with quantum mechanics, and often predict additional spatial dimensions and complex space-time structures. Within string theory, for example, the concept of higher dimensional wormholes or brain world scenarios has been proposed, where our observable universe is embedded in a higher dimensional space connected by wormhole-like passages. Historically, the wormhole concept has evolved alongside our growing understanding of black holes and the structure of the universe. While Einstein and Rosen's initial work was largely mathematical and abstract, modern theoretical physics has brought wormholes into conversations about the fundamental nature of reality, the topology of the universe, and the potential existence of a multiverse. These ideas have not been without controversy, as some physicists argue that wormholes are artifacts of mathematical idealizations rather than physical entities. Others remain optimistic, motivated by the sheer elegance and consistency of the equations that allow for such solutions. Experimental efforts to detect signatures of wormholes or their effects remain in their infancy, given the enormous technical and observational challenges involved. Nevertheless, wormholes continue to inspire theoretical and philosophical inquiry. They invite us to reconsider the limitations of space and time, to imagine pathways connecting distant realms, and to question whether black holes might serve as conduits rather than endpoints. This conceptual wormholes also provoke deeper questions about the nature of causality and the structure of space-time itself. If such tunnels exist and can connect not only distant spatial points but different times, this introduces potential causal loops, commonly known as time travel paradoxes. For example, scenarios arise where an effect might precede its cause, challenging the foundational logic underlying physics. Physicists have proposed mechanisms like the chronology protection conjecture, suggested by Stephen Hawking, which theorizes that the laws of physics might prevent the formation of closed time-like curves and thus preserve causal order, effectively prohibiting time travel through wormholes. Despite these theoretical safeguards, the mathematical possibility of traversable wormholes remains an active field of study. Some physicists speculate that if exotic matter could be harnessed or created, even on a microscopic scale, it might stabilize tiny wormholes at the quantum level, which could serve as conduits for quantum information or particles. These microscopic wormholes might link disparate regions of space-time, subtly influencing phenomena such as quantum entanglement or the fabric of space-time at the Planck scale. Further, wormholes have found a fascinating role in the burgeoning field of the holographic principle and the ADS-CFT correspondence, where researchers explored dualities between theories of gravity in higher dimensional spacetimes and quantum field theories on lower dimensional boundaries. In some models, wormhole geometries emerge naturally, offering insights into quantum gravity and information paradoxes related to black holes. These developments illustrate how wormholes serve as a powerful conceptual tool, bridging general relativity, quantum mechanics, and information theory. In addition to their theoretical significance, wormholes have permeated popular culture, fueling science fiction stories and speculative ideas about interstellar travel and multiverse exploration. While these cultural representations often simplify or exaggerate the physics involved, they reflect a genuine human fascination with the possibility of transcending the apparent limits of space and time. However, the challenges remain formidable. Exotic matter required to hold wormholes open violates known energy conditions and has not been observed in nature. Even if such matter exists, the amount and stability needed for macroscopic wormholes would be extraordinary. Moreover, the Immense tidal forces near wormhole throats might destroy any traveler attempting to pass through, unless the wormhole structure differs significantly from classical models. From the standpoint of black hole physics, the prospect that black holes might connect to wormholes suggests a radical rethinking of their role in the universe. Instead of being mere destructive endpoints, black holes could be portals or junctions within a larger cosmic network. This idea aligns with certain multiverse theories, which propose that our universe is just one among many, possibly connected through such wormhole-like structures. In this context, black holes become more than astrophysical curiosities. They may represent conduits to entirely new realms of existence. Exploring these ideas further leads to profound philosophical and scientific implications. If wormholes or black hole gateways exist, what lies beyond them? Could they provide a pathway to other universes with different physical laws or dimensions? How would information and matter behave during such transitions? These questions remain open and challenge the boundaries of current knowledge. In sum, wormholes embody one of the most captivating theoretical constructs emerging from Einstein's general relativity, blending deep mathematics with speculative cosmology. While firmly rooted in the equations governing spacetime, their physical reality remains unproven. Nevertheless, wormholes form a crucial part of the dialogue about black holes as potential gateways, providing a conceptual scaffold for imagining how the most enigmatic objects in the universe might connect to realms beyond our current understanding. In the vast realm of physics, few mysteries have captivated scientists as intensely as the challenge of reconciling quantum mechanics with general relativity. Each framework dominates its own domain. Quantum mechanics governs the behavior of the very small, describing particles and forces with astonishing precision, while general relativity reigns supreme over the cosmic scale, explaining gravity and the curvature of spacetime itself. Yet black holes stand at the intersection of these two regimes, presenting a unique and profound conundrum. These dense cosmic entities warp spacetime to such extremes that understanding their true nature demands a unified theory of quantum gravity, theory that remains elusive but is fundamental to unraveling black hole mysteries. At the heart of the issue lies the incompatibility of the classical picture of black holes, as described by Einstein's theory of general relativity, with the probabilistic nature of quantum mechanics. According to general relativity, a black hole is defined by a singularity, a point of infinite density, where known physical laws break down, enshrouded by an event horizon, a boundary beyond which nothing can escape. However, quantum theory, which excels at describing particles and their interactions on the smaller scales, challenges this simplistic notion. It predicts phenomena that seem to conflict with the classical description, especially regarding the fate of information that crosses the event horizon. One of the most significant puzzles is the so-called black hole information paradox. Quantum mechanics asserts that information about the physical state of a system cannot be destroyed, a principle known as unitarity. However, if matter falls into a black hole and is lost forever as the black hole evaporates through Hawking radiation, as classical interpretations suggest, this would violate the fundamental precept of quantum mechanics. This paradox has stimulated decades of debate and theoretical work, pushing physicists to reconsider assumptions and to explore new frameworks that might reconcile these divergent principles. Hawking radiation itself, predicted in the mid-1970s by Stephen Hawking, was a groundbreaking insight blending quantum theory and gravity. Hawking proposed that black holes are not entirely black, but emit a faint glow due to quantum effects near the event horizon. Particle-antiparticle pairs constantly flicker into existence in the quantum vacuum. Sometimes, one particle falls into the black hole while the other escapes, creating the appearance that the black hole emits radiation. This process implies that black holes can lose mass and eventually evaporate completely over incredibly long timescales. While this discovery suggested that black holes are not eternal prisons, it deepened the information paradox because the radiation seems to carry no information about the matter that formed the black hole or fell into it. If a black hole disappears and only this featureless radiation remains, what happened to the information encoded in the initial material? This fundamental question remains unresolved and lies at the heart of attempts to formulate a quantum theory of gravity. Two prominent candidate theories aiming to unify quantum mechanics and general relativity, and thereby address the black hole puzzles, are string theory and loop quantum gravity. Each offers distinct approaches and insights into the nature of space-time and black holes. String theory proposes that the fundamental constituents of reality are not point particles, but rather tiny, vibrating one-dimensional strings. These strings can oscillate in various modes, manifesting as different particles. Crucially, string theory naturally incorporates gravity and predicts extraspatial dimensions beyond the familiar three. This framework provides tools to analyze black holes in a quantum context, often using the idea that black holes can be modeled as complex bound states of strings and brains's multidimensional objects. These models have succeeded in reproducing key thermodynamic properties of certain black holes, such as entropy, linking microscopic string states with macroscopic black hole characteristics. This connection is a major success of string theory and offers hope that it might resolve the information paradox. Moreover, string theory suggests intriguing ideas about black hole interiors and event horizons. The fuzzball proposal posits that what we perceive as a black hole with a smooth horizon is, at a fundamental level, a quantum fuzz of strings and brains without a traditional horizon or singularity. If true, this could mean information is not lost but encoded in the complex quantum structure replacing the classical black hole interior. On the other hand, loop quantum gravity (LQG) approaches the problem from a different angle. Instead of introducing new fundamental objects like strings, LQG attempts to quantize space-time itself, breaking it down into discrete, quantized chunks or loops. This quantization leads to a picture where space and time have a granular structure at the Planck scale, potentially removing the problematic singularities that plague classical black holes. LQG models predict that the classical singularity is replaced by a quantum bounce or bridge, possibly connecting to another region of spacetime. Such a bridge could be interpreted as a wormhole or a passage to another universe, offering a theoretical basis for the idea that black holes might be gateways rather than dead ends. This notion is speculative, but consistent with some solutions in LQG that describe Planck stars, ultradense, quantum objects that avoid singularity, collapse, and might rebound or tunnel into a different spacetime. These advances have crucial implications for understanding whether black holes connect to other universes. While the classical view sees the event horizon as an impenetrable boundary, quantum gravity effects suggest it might be more permeable, or that the interior structure is far richer than previously imagined. The information paradox acts as a litmus test for these theories. Any successful quantum gravity theory must explain how information is preserved and possibly transmitted beyond the event horizon. One of the most profound theoretical developments related to this is the holographic principle, which emerges from string theory and black hole thermodynamics. The principle posits that all the information contained within a volume of space can be described by data on its boundary, much like a hologram encodes a three-dimensional image on a two-dimensional surface. Applied to black holes, this suggests that the information about everything that falls in might be encoded on the event horizon itself, resolving the paradox by preserving information in a non-local way. This holographic encoding challenges traditional intuitions about space and locality and is at the frontier of current research. Despite these exciting ideas, much remains uncertain. Quantum gravity theories are mathematically intricate and lack definitive experimental tests, especially for black holes, which are distant and extreme astrophysical objects. Hawking radiation has yet to be observed directly due to its incredibly faint nature compared to other cosmic signals. Moreover, the full quantum description of realistic black holes, including their formation, evaporation, and interaction with their environment, is still incomplete. Furthermore, these unresolved issues ripple out into other realms of physics, influencing cosmology and the quest for a theory of everything. If black holes are gateways or connect to other universes, this would revolutionize our understanding of reality itself, with profound philosophical and scientific consequences. It would suggest that the cosmos is far more interconnected and dynamic than classical physics allowed, blurring the lines between what is inside and outside, here and elsewhere. In the meantime, physicists continue to explore various theoretical avenues, employing mathematical tools and thought experiments to inch closer to a quantum theory of gravity that explains black holes fully. This endeavor brings together the deepest insights of 20th and 21st century physics, challenging foundational assumptions and inspiring new concepts that could reshape our worldview. The notion that our universe might not be the only one has evolved from philosophical speculation into a serious scientific hypothesis, driven by advances in cosmology and theoretical physics. The idea of a multiverse, a vast collection of universes existing beyond our observable cosmos, stands as one of modern cosmology's boldest and most transformative proposals. While this concept stretches the imagination and challenges traditional notions of reality, it has its roots in historical reflections on the nature of existence and has become increasingly supported by theoretical frameworks developed over the last century. Historically, the concept of multiple worlds is not new. Ancient philosophers like Democritus and Epicurus proposed that countless worlds might exist, scattered through infinite space. These early ideas, while lacking scientific rigor, planted seeds for later considerations. During the Enlightenment and beyond, the discussion about infinite or multiple universes continued philosophically, but remained largely speculative, often intertwined with metaphysical or theological implications. It was only with the advent of modern cosmology and the discovery of the expanding universe in the early 20th century that scientists began to develop mathematical and empirical models capable of describing the cosmos on grand scales. The Big Bang theory, formalized in the 1920s and supported by observational evidence such as cosmic microwave background radiation and galactic redshifts, provided a foundational picture of a universe that had a beginning and has been evolving since. Yet, this model, while incredibly successful, opened new questions about the conditions preceding the Big Bang and the nature of the cosmos beyond what we can observe. one of the key breakthroughs in modern cosmology that gave rise to multiverse theories is the development of inflationary cosmology during the 1980s, proposed initially by Alan Guth and further refined by Andre Linde and others. Inflation posits that the universe underwent a brief but stupendously rapid exponential expansion immediately after the Big Bang. This inflationary phase stretched space-time so drastically that it explains the large-scale uniformity and flatness of the universe, as well as the origin of small density fluctuations that led to galaxy formation. More intriguingly, inflationary theory also opens the door to the idea of a multiverse. In many models, inflation does not occur uniformly or only once. Instead, inflation can be eternal, with pockets of space-time continuing to inflate and spawn bubble universes, each potentially having different physical constants and laws. These bubble universes are causally disconnected from one another, meaning no information or matter can travel between them, rendering each a separate cosmos. Such a multiverse is vast, perhaps infinite, with each universe representing a unique realization of physical parameters. This framework helps address some puzzling fine-tuning problems, where the constants of nature in our universe appear delicately balanced to allow the existence of complex structures and life. In a multiverse setting, our universe is simply one of many, and it is unsurprising that we find ourselves in one compatible with life. An application of the anthropic principle. String theory, a leading candidate for a theory of everything that aims to unify all fundamental forces and particles, further strengthens the multiverse hypothesis. String theory's mathematical landscape is famously vast, encompassing a multitude of possible vacuum states, suggest numbers as high as 500 different solutions. Each vacuum state corresponds to a distinct set of physical laws, particle spectra, and dimensional shapes. This string landscape implies a huge variety of possible universes, each realized by different ways the extra dimensions compactify and the strings vibrate. Within this enormous landscape, the question arises, how is our particular universe selected? One answer lies again in cosmological inflation, where different vacuum states might be realized in different regions of the multiverse. The coupling of inflation and the string landscape creates a picture where numerous universes bubble forth, each embodying one solution from the landscape, thereby explaining the observed diversity of physical realities. The implications of this hypothesis are profound. It reframes our cosmic address from a unique, privileged standpoint to one possibility among countless others. Our familiar laws of physics might be local environmental phenomena rather than universal truths. This shifts the quest in physics from seeking a single set of laws to understanding the statistical distribution of universes in the multiverse and how observers emerge within them. Crucially, the multiverse concept intersects intriguingly with the idea of black holes as possible gateways between universes. If black holes indeed represent connections or transitions to other regions of spacetime or other universes, they might provide a physical mechanism bridging individual universes within the multiverse. While this remains speculative, some theories propose that the interior of black holes could harbor nascent universes born from gravitational collapse, thus making black holes cosmic seeds rather than ultimate endpoints. In such scenarios, each black hole would function as a portal, linking our universe to another bubble universe with potentially different properties. This hypothesis, sometimes termed the fecund universes idea, was notably explored by physicist Lee Smolin, who suggested that universes might reproduce through black holes. with natural selection favoring universes that produce more black holes. This evolutionary cosmology conjecture provides an innovative framework to explain the apparent fine-tuning of constants by positing a cosmic reproduction cycle. From the viewpoint of inflationary cosmology and string theory, these black hole gateways would be embedded within the grand multiverse structure, mediating transitions or births of universes within the broader cosmic tapestry. Such a mechanism also addresses the conundrum of the initial conditions of our universe, as it might have originated from the interior of a black hole in a parent universe, thus avoiding the need for a singular beginning in the traditional sense. While alluring, these ideas face significant challenges. Testing the multiverse and black hole gateway hypotheses is difficult given their inherent unobservability. Other universes, by definition, lie beyond the reach of our instruments, and any signal crossing black hole event horizons remains inaccessible. Nonetheless, theoretical advances and indirect observations, such as detailed measurements of the cosmic microwave background or gravitational waves, may provide clues supporting or constraining these models. Moreover, the mathematical consistency and elegance of string theory, inflation, and related frameworks inspire confidence in their validity. They offer explanations not only for the multiverse, but for fundamental puzzles in particle physics and cosmology, such as dark energy, dark matter, and the hierarchy problem. The multiverse emerges not merely as speculation, but as a consequence of deeply grounded theoretical structures. Philosophically, the multiverse hypothesis invites profound reflection on the nature of scientific explanation and the limits of empirical verification. If multiple universes exist but cannot be directly observed, what does this mean for the scientific method? Some argue that the multiverse represents a paradigm shift, requiring new approaches to evidence and inference, possibly expanding the domain of science to include mathematical consistency and explanatory power as criteria alongside observation. The concept of a multiverse also resonates with cultural and existential questions about humanity's place in the cosmos. It challenges anthropocentric views and the notion of a singular cosmic narrative, replacing them with a vast, rich panorama of realities, some possibly wildly different from our own. This cosmic pluralism aligns with emerging trends in physics, where the universe is no longer seen as an isolated system, but as part of an interconnected, multidimensional whole. As research advances, physicists continue to probe the boundaries of these ideas, exploring their mathematical foundations, physical implications, and potential observational signatures. Black holes remain central to these efforts, serving as laboratories for extreme physics where quantum gravity effects become manifest, and where connections to other universes might one day be glimpsed. Thus, the multiverse hypothesis stands as a testament to human curiosity and the drive to comprehend the ultimate nature of reality. It stretches the imagination while rooted in rigorous theory, weaving together strands from ancient philosophy to cutting-edge physics. In linking cosmology, quantum gravity, and black hole science, it illuminates a vast and mysterious cosmos, possibly teeming with countless universes, of which our own is but one. Beyond theoretical motivations, some physicists explore indirect ways to probe the multiverse hypothesis. Although other universes lie beyond direct observation, subtle imprints on our universe could provide clues. For example, certain models suggest that collisions between bubble universes during inflation might leave faint signatures in the cosmic microwave background. Radiation, the afterglow of the Big Bang that we can measure, Researchers analyze this radiation for anomalies or patterns that could hint at such cosmic encounters, though no conclusive evidence has yet been found. Similarly, gravitational waves, ripples in spacetime produced by cataclysmic events, might carry information about physics beyond our universe. Future gravitational wave observatories could detect signals originating from processes linked to other universes or from early universe dynamics shaped by the multiverse framework. Such indirect probes could strengthen the scientific grounding of multiverse theories. Critically, these efforts emphasize the interplay between the multiverse and the nature of scientific inquiry. Traditionally, empirical testability has been the hallmark of scientific validity. The multiverse challenges this criterion by suggesting realms inherently beyond observational access. This has sparked debate among scientists and philosophers about the role of theory, mathematics, and prediction in defining science. Some argue for a broader understanding of scientific explanation that includes explanatory coherence and mathematical consistency, especially in fields where direct observation is limited or impossible. At the same time, the multiverse encourages new ways of thinking about probability and typicality in cosmology. If countless universes exist with varied physical laws, what does it mean to say that our universe is typical or special? This question influences how predictions are made and how anthropic reasoning is applied using the fact of our existence as a selection effect in the multiverse ensemble. The implications of the multiverse extend even into fundamental metaphysical questions. If reality comprises an unimaginably vast collection of universes, each with its own reality and history, the notion of a singular, unique universe loses ground. This cosmic pluralism resonates with ideas in philosophy and even theology, while grounding itself firmly in physical theory. It invites us to reconsider the meaning of existence and our cosmic significance. Returning to the connection with black holes, these enigmatic objects provide a physical context where multiverse ideas might find realization. The suggestion that black holes might be portals or seeds of new universes offers a mechanism linking microcosmic gravitational phenomena with the macrocosmic multiverse. This idea blurs the boundaries between creation and destruction, where the death of matter in one universe might give birth to another, perpetuating an endless cosmic cycle. In summary, the multiverse hypothesis stands at the forefront of cosmological thought, weaving together deep historical reflections, sophisticated theoretical frameworks, and profound philosophical questions. It challenges our perceptions of reality and pushes the boundaries of scientific exploration, all while offering tantalizing possibilities that black holes might serve as gateways in this vast cosmic landscape. Black holes have long captured the imagination of both scientists and the public, not merely as cosmic sinkholes from which nothing can escape, but as mysterious objects that might play a far more dynamic role in the fabric of the universe. Over the decades, as theoretical physics has advanced, the idea that black holes could serve as gateways or portals, connecting different regions of space-time or even different universes, has gained traction. This notion, once purely speculative, has been bolstered by contributions from some of the most renowned physicists, including Kip Thorne and Stephen Hawking, who have proposed frameworks in which black holes might link to alternate realities or manifest as their hypothetical counterparts. White holes, the traditional picture of a black hole, established by solutions to Einstein's field equations in general relativity, depicts a region of space-time where gravity is so intense that it forms an event horizon, a boundary beyond which escape is impossible. At the core, lies a singularity, a point where density and space-time curvature become infinite, and known laws of physics cease to apply. This classical description, though mathematically elegant, leaves many questions unresolved, especially regarding what lies beyond the event horizon and how quantum effects might alter this picture. Kip Thorne, a leading expert in gravitational physics and a Nobel laureate, has been at the forefront of exploring exotic phenomena associated with black holes. In particular, Thorne has extensively studied wormholes, hypothetical bridges connecting distant points in spacetime. Wormholes, also called Einstein-Rosen bridges, were first theorized in the early 20th century as solutions to the equations of general relativity. These bridges could, in theory, allow for shortcuts through spacetime, possibly connecting different universes or regions of the same universe. Thorne proposed that wormholes might be stabilized by exotic matter possessing negative energy density, which is required to prevent the bridge from collapsing instantly, although such matter has not been observed. Quantum field theory allows for phenomena like the Casimir effect that suggest negative energy densities are possible in certain contexts. If wormholes could exist and remain open, black holes might serve as one end of these bridges, with their counterparts white holes acting as the exit points. White holes are theoretical objects that behave as the time-reversed version of black holes. Instead of swallowing matter and light, white holes would expel them, prohibiting anything from entering. While no observational evidence for white holes currently exists, their existence is allowed by the equations of general relativity, and they emerge naturally in the mathematical extensions of black hole solutions, such as the maximally extended Schwarzschild solution. This leads to a fascinating speculation. Black holes in our universe might connect through wormholes to white holes in alternate universes or other regions of spacetime. Matter and information swallowed by a black hole could, in principle, re-emerge from a white hole, preserving unitarity and solving the black hole information paradox. This speculative picture transforms black holes from cosmic endpoints into dynamic conduits bridging different realities. Stephen Hawking, famous for discovering black hole radiation, also contributed nuanced perspectives on these ideas. Although he was initially skeptical about wormholes as practical bridges, Hawking explored the possibility that quantum effects might render the black hole interior far more complex than classical physics suggests. Hawking's no-boundary proposal, and later reflections on the firewall paradox, illustrate the evolving understanding of event horizons and the fate of information inside black holes. Hawking, radiation itself implies that black holes evaporate over time, raising questions about what happens to the information contained within. Some speculative models propose that the endpoint of black hole evaporation might be a white hole, ejecting the trapped information back into the universe. In this view, black holes and white holes form a complete cycle, with black holes acting as entry points and white holes as exit portals. Beyond the frameworks proposed by Thorne and Hawking, various speculative models have emerged over recent decades, exploring black holes as possible gateways in the multiverse or as seeds for new universes. For instance, the concept of black hole cosmology suggests that the interior of a black hole could undergo a bounce or phase transition, leading to the birth of a baby universe expanding inside it. This model aligns with ideas from loop quantum gravity, which posits that quantum effects resolve classical singularities, replacing them with quantum bridges or Planck stars. Such baby universes would be causally disconnected from their parent universe, but might inherit physical constants influenced by the black hole's formation conditions. This scenario suggests a cosmological natural selection, where universes producing more black holes generate more offspring, potentially explaining fine-tuning of physical laws. Despite the compelling elegance of these models, numerous challenges remain. The first is the lack of observational evidence. Black holes, especially their interiors, are notoriously difficult to probe. The event horizon prevents any direct observation of what occurs inside, and current astronomical instruments can only detect indirect signals such as gravitational waves, X-ray emissions, and shadows cast on surrounding matter. Secondly, stabilizing a wormhole requires exotic matter with properties not yet confirmed in the lab or in astrophysical observations. Without such matter, wormholes would collapse too rapidly for travel or information transfer. Quantum gravity remains the key to understanding if such exotic states could exist and maintain stable wormholes. Thirdly, the quantum description of black holes is incomplete. While string theory and loop quantum gravity offer promising approaches, a consensus on the true quantum nature of black holes remains out of reach. The information paradox and firewall paradox highlight tensions between quantum mechanics and general relativity that any successful theory must resolve. Moreover, the concept of white holes, while mathematically consistent, raises causal and thermodynamic puzzles. White holes violate the second law of thermodynamics by decreasing entropy and would appear as highly unstable objects if they existed. Explaining their formation and stability within known physics remains a significant hurdle. Finally, even if black holes connect to other universes, the mechanisms for information or matter transfer across such bridges and, whether they preserve causality and coherence, are still largely conjectural. The challenge lies in formulating testable predictions and devising experiments or observations capable of confirming or falsifying these ideas. In recent years, advances in observational astronomy, such as the Event Horizon Telescope's imaging of black hole shadows and the detection of gravitational waves from black hole mergers, have begun to shed light on black hole properties. Although these observations do not yet reveal internal structure or possible connections to other universes, they constrain theoretical models and help refine our understanding of black hole physics. Cutting-edge research also investigates analogues of black holes in laboratory settings, such as sonic black holes in Bose-Einstein condensates, where Hawking-like radiation can be studied experimentally. These analogues provide valuable insights into quantum effects near horizons and might eventually inform theories about real astrophysical black holes. In sum, the idea that black holes might act as portals to other universes remains a captivating frontier of modern physics. It straddles the boundary between rigorous mathematical theory and imaginative speculation, motivated by attempts to reconcile gravity with quantum mechanics and to solve deep puzzles like the information paradox. While the evidence is far from conclusive, the ongoing dialogue among physicists like Kip Thorne, Stephen Hawking, and others continues to inspire innovative models and experimental efforts, gradually illuminating the shadowy realms within and beyond black holes. The study of black holes, once confined primarily to theoretical physics, has entered a new era propelled by remarkable advances in observational technology. In recent years, the convergence of innovative telescopes, gravitational wave detectors, and high-performance computational techniques has allowed scientists to explore black holes not just as mathematical curiosities, but as tangible astrophysical objects. This progress opens the door to probing some of the most profound questions about black holes' nature and, potentially, their role as gateways to other universes. The Event Horizon Telescope, EHT, a global network of synchronized radio observatories, marked a turning point by capturing the first ever image of a black hole's shadow. In 2019, the EHT collaboration revealed the silhouette of the supermassive black hole at the center of galaxy M87, approximately 55 million light-years away. This achievement confirmed the existence of event horizons, the defining feature of black holes, and provided direct empirical support for general relativity's predictions under extreme gravitational conditions. The EHT image is not merely a static photograph, but a complex dataset obtained through very long baseline interferometry via. This technique synthesizes observations from telescopes spread across Earth, effectively creating a planet-sized aperture capable of resolving structures at scales smaller than our solar system, by capturing radiation emitted by hot plasma swirling. Near the event horizon, the EHT offers insights into the accretion processes, magnetic fields, and relativistic effects at play near black holes. While the EHT has revolutionized black hole imaging, it currently reveals only the immediate environment. Outside the event horizon, the nature of what lies within remains obscured by the horizon's causal boundary, limiting direct observational access. However, the detailed structure and dynamics of the accretion disk and relativistic jets provide indirect information about the black hole's spin, mass, and possible deviations from classical models, parallel to imaging efforts. Gravitational wave observatories have opened a complementary window into black hole physics. Facilities such as LIGO Laser, Interferometer, Gravitational Wave Observatory, and Virgo have detected gravitational waves, minute ripples in space-time generated by the mergers of black holes and neutron stars. These signals carry information about the masses, spins, and orbital dynamics of the colliding objects, allowing tests of general relativity in the strong field regime. The detection of gravitational waves has confirmed the existence of binary black hole systems and provided precise measurements of their properties. This data constrains models of black hole formation and evolution and offers a novel avenue for exploring exotic phenomena, including the possibility of primordial black holes formed in the early universe or black holes with unexpected properties. Importantly, gravitational wave signals also offer a potential route to detect signs of black holes, connecting to other universes or exotic structures like wormholes. Some theoretical proposals suggest that echoes in the gravitational waveforms, delayed reflections caused by modifications near the event horizon, could indicate departures from classical black hole models, hinting at quantum gravitational effects, or the presence of a wormhole throat. Although such echoes remain tentative and controversial, ongoing analysis of gravitational wave data aims to improve sensitivity and identify subtle features that may provide evidence for physics beyond standard black hole paradigms. Upcoming upgrades to LIGO, Virgo, and the launch of new observatories like Kagra in Japan and LISA, Laser Interferometer Space Antenna in space, promise to extend detection ranges and frequency bands, enhancing prospects for discovering such signatures beyond electromagnetic and gravitational observations. Other experimental approaches seek to explore black hole analogues in laboratory conditions. Sonic black holes, created by manipulating sound waves in ultra-cold atomic gases, mimic event horizons, and allow observation of Hawking-like radiation in controlled settings. These analog systems serve as testbeds for understanding horizon physics, quantum effects, and information flow, potentially informing interpretations of astrophysical black holes. Despite these advances, significant challenges remain in observing direct evidence of black holes as portals or gateways to other universes. The causal barrier imposed by the event horizon fundamentally limits what information can escape from within, constraining observational possibilities. Moreover, phenomena such as wormholes or white holes, if they exist, may involve physics at scales currently inaccessible or require detection of exotic particles or energies beyond present capabilities. Another limitation arises from the vast distances and timescales involved. Black holes, especially supermassive ones at galactic centers, lie millions or billions of light-years away, making detailed observations difficult. Transient events like black hole mergers produce signals that must be captured and analyzed rapidly and accurately, requiring sophisticated instrumentation and data processing. Looking forward, future technological advancements hold promise for overcoming some of these barriers. The planned expansion of the Event Horizon Telescope network aims to improve image resolution and capture dynamic changes in black hole environments. Integrating more telescopes, including those in space, could enable real-time movies of accretion flows and jet formations, revealing new details about black hole behavior. Gravitational wave astronomy will enter a new phase with space-based detectors like LISA, designed to detect lower frequency waves from supermassive black hole mergers and other exotic sources. This expanded observational window could uncover previously hidden populations of black holes and test theories of quantum gravity and multiverse connections. Additionally, advances in neutrino detection and high-energy cosmic ray observatories may reveal complementary signals related to black hole phenomena, offering multi-messenger astrophysics perspectives. By combining data across electromagnetic, gravitational, neutrino, and cosmic ray channels, scientists can build a more complete picture of black hole environments and their possible interactions with other universes. Theoretical developments also guide observational strategies. Predictions about signatures of black hole portals, such as specific gravitational wave echoes or unusual particle emissions, help focus experimental efforts. Machine learning and artificial intelligence techniques increasingly assist in analyzing vast and complex datasets, identifying subtle patterns that might otherwise be overlooked. Ultimately, the quest to find observational evidence linking black holes to other universes intersects deeply with the limits of human knowledge and technological ingenuity. The boundary between speculative theory and empirical science is narrowing, as instruments become ever more capable of testing bold ideas, while definitive proof remains elusive. The continuous interplay between observation and theory drives progress. The exploration of black holes and their possible role as cosmic portals exemplifies the spirit of scientific inquiry. Rigorous mathematics, sophisticated technology, and imaginative hypotheses. As we push the frontiers of observation, we edge closer to answering profound questions about the nature of reality, the structure of the cosmos, and the potential interconnectedness of multiple universes. The concept of black holes as gateways to other universes invites more than just scientific inquiry. It penetrates deeply into the philosophical fabric of how we understand reality, existence, and causality. The possibility that these cosmic objects might connect disparate realms challenges long-held notions about the nature of the universe and our place within it, provoking profound reflection on what constitutes reality itself. Philosophically, black hole gateways question the uniqueness and completeness of our observable universe. Classical views of reality often assume a singular, all-encompassing cosmos governed by universal laws. Yet, if black holes serve as portals to alternate universes or dimensions, then reality expands into a pluralistic landscape, a multiverse, where countless versions of existence coexist. This plurality unsettles the traditional monistic worldview, opening the door to an ontological framework that accommodates infinite diversity. This ontological shift also impacts how we understand causality. In our familiar world, cause and effect follow a temporal sequence constrained by the speed of light, preserving the chronological order of events. But wormholes or black hole gateways imply shortcuts in space-time, potentially permitting connections or even time loops. The possibility of closed time-like curves, where an event might influence its own cause, has been explored theoretically, raising paradoxes such as the grandfather paradox and challenging linear notions of time. These paradoxes invite reconsideration of causality's foundational role. Some physicists and philosophers argue that the laws governing these exotic structures may enforce consistency constraints, preventing paradoxical outcomes, while others speculate that new physics may reveal fundamentally different causal structures. Beyond classical intuition, another philosophical question concerns the nature of existence and identity across universes. If black holes connect to other universes with different physical laws and histories, what does it mean for something to exist there versus here? Does identity persist across these bridges, or do we encounter wholly separate realities? The idea of universe branching, common in interpretations of quantum mechanics, like the many worlds interpretation, suggests a vast multiplicity of selves and histories, fracturing the classical notion of a singular, continuous identity. Culturally, the imagery and symbolism of black holes as gateways have captivated human imagination, influencing literature, art, and popular media. From early science fiction tales to modern cinematic epics, black holes often serve as metaphors for mystery, transformation, and the unknown. They embody thresholds between worlds, inviting journeys into alternate dimensions or new states of consciousness. Science fiction writers have long exploited the concept of black holes to explore themes of exploration, existential risk, and transcendence. Works such as Carl Sagan's Contact and Christopher Nolan's Interstellar incorporate black hole gateways to probe humanity's place in a vast and possibly interconnected cosmos. These narratives reflect and shape public fascination with black holes, bridging scientific ideas and cultural expression. The symbolism of black holes resonates with ancient mythological motifs, such as portals to the underworld or cosmic gateways, connecting different planes of existence. In many cultures, thresholds symbolize transformation and passage, echoing the scientific notion of black holes as passages to new realities. This archetypal significance enriches the cultural dialogue around black holes, blending scientific discovery with human storytelling traditions. The influence of black hole gateway concepts extends to philosophy of mind and consciousness studies. Speculative theories propose that traversing or interacting with such portals could alter perception or consciousness itself, raising questions about subjective experience and its relationship to physical reality. The possibility of alternate universe's challenges assumptions about the finality of death and the uniqueness of life, inspiring philosophical speculation on immortality and identity continuity. Moreover, the notion of black holes as cosmic bridges has philosophical implications. For epistemology, the theory of knowledge, if parts of reality lie beyond direct observation, connected through black hole gateways or multiverse channels, then what can we claim to know? This challenges empirical science's traditional limits and suggests the need for expanded frameworks, accommodating indirect inference, mathematical consistency, and theoretical coherence as means of understanding reality. The tension between empirical verification and theoretical speculation embodied in black hole gateway hypotheses mirrors broader epistemic challenges in modern physics. The debate over the multiverse and related ideas exemplifies this, raising questions about the criteria for scientific legitimacy and the scope of human knowledge. Historically, the progression of scientific understanding has repeatedly expanded. Humanity's conception of the cosmos from geocentrism to heliocentrism, from a static universe to an expanding one, and now to a possible multiverse connected by black holes. Each paradigm shift has disrupted established worldviews, provoking philosophical and cultural upheavals. Black hole gateways continue this tradition, representing the frontier of cosmic understanding. Finally, the profound mysteries surrounding black holes and their potential as portals foster a sense of wonder and curiosity fundamental to human nature. They exemplify the interplay between the known and the unknown, the tangible and the speculative, inspiring both rigorous scientific pursuit and creative imagination. The captivating idea that black holes might function as gateways to other universes has sparked considerable debate within the scientific community. While this concept appeals to our imagination and offers intriguing resolutions to some deep theoretical puzzles, it also faces substantial challenges and criticisms. Many physicists approach these proposals with healthy skepticism, emphasizing the importance of empirical evidence, physical plausibility, and theoretical consistency. Exploring these scientific objections reveals the rigorous standards that extraordinary claims must meet to transition from speculation to accepted science. One of the primary challenges confronting black hole gateway theories is the physical constraints imposed by known laws of physics. According to classical general relativity, black holes possess event horizons that act as one-way boundaries. Nothing, not even light or information, can escape once it crosses the horizon. This causal barrier inherently limits any communication or travel from inside the black hole to other regions or universes. The very nature of the event horizon renders it a seemingly insurmountable obstacle for any passage, calling into question how black holes could realistically serve as portals. Furthermore, the singularities predicted at black hole centers represent regions where densities become infinite and space-time curvature diverges without bound. These singularities indicate breakdowns of classical physics, suggesting that the known laws cannot adequately describe what happens within. Without a complete and consistent quantum theory of gravity, it remains uncertain whether singularities can be resolved in a manner compatible with traversable gateways. This lack of a fully developed theory undermines confidence in models positing black holes as stable bridges to other universes. Closely related to this is the problem of stability and traversability. Wormholes and other proposed black hole portals typically require exotic matter or energy with negative energy density to prevent collapse. Such exotic matter violates known energy conditions in general relativity, and while quantum effects like the Casimir effect, produce negative energy densities in limited contexts. Scaling this to astrophysical objects remains speculative. The absence of confirmed sources or mechanisms for sustaining stable wormholes casts doubt on their physical realizability. In addition to these theoretical issues, the conspicuous lack of empirical evidence stands as a significant barrier. Observational astronomy and astrophysics have made tremendous strides in detecting and characterizing black holes, yet no direct or indirect observations to date conclusively indicate that black holes connect to other universes or function as gateways. The signals detected, such as gravitational waves from mergers or electromagnetic emissions from accretion disks, are consistent with black holes as predicted by classical general relativity and do not exhibit anomalies suggestive of exotic connections. Some proponents suggest that phenomena like gravitational wave echoes might provide subtle clues to such exotic structures, but these signals remain tentative and contentious. The difficulty in distinguishing potential signatures of black hole gateways from noise or conventional astrophysical processes complicates attempts at empirical verification. This observational ambiguity fuels skepticism and underscores the need for more robust, testable predictions. Mainstream physicists also raise concerns about the interpretative frameworks used to justify black hole gateway ideas. Theoretical models often rely heavily on mathematical extensions or idealized solutions that may lack physical relevance. For example, the maximally extended Schwarzschild solution includes white holes and wormholes, but these features may be artifacts of idealized conditions, absent in realistic astrophysical black holes formed from stellar collapse. This raises questions about the applicability of such solutions to actual black holes. Moreover, alternative explanations rooted in established physics provide competing accounts for phenomena attributed to black hole gateways. For instance, the black hole information paradox, a key motivation for considering wormholes or white holes, has inspired various approaches within quantum gravity and holographic principles that do not require exotic space-time bridges. These include ideas such as black hole complementarity and the firewall hypothesis, which aim to reconcile information preservation with quantum mechanics without invoking portals to other universes. Some critics argue that invoking black hole gateways ventures too far into speculative metaphysics, straining the boundaries of empirical science. While imaginative and conceptually rich, such ideas risk detachment from falsifiability, a cornerstone of scientific methodology. Without clear experimental or observational criteria, these hypotheses may remain in the realm of philosophy rather than physics. Nonetheless, scientific skepticism does not preclude openness to new ideas. Rather, it demands rigorous scrutiny and demands that extraordinary claims meet extraordinary evidence. This stance drives the continued refinement of theoretical models, improved observational techniques, and experimental innovations aimed at testing the boundaries of our understanding. Interestingly, this skepticism has led to productive dialogue and progress. By critically examining the assumptions and limitations of black hole gateway theories, physicists deepen their grasp of black hole physics, quantum gravity, and cosmology. Such challenges motivate the search for a consistent quantum theory of gravity and encourage the development of novel observational strategies. Furthermore, alternative viewpoints highlight the diversity of thought within the scientific community. Some researchers emphasize that current limitations in observation and theory should not prematurely dismiss bold ideas. advocating for a pluralistic approach to exploring the unknown. They argue that even if black hole gateways remain unproven, their investigation stimulates creativity and interdisciplinary collaboration. In conclusion, the scientific skepticism surrounding black holes as portals to other universes reflects a healthy and necessary process within the scientific endeavor. It acknowledges profound theoretical and empirical challenges, underscores the rigor required for acceptance, and promotes ongoing inquiry. While black hole gateways remain tantalizing possibilities, the path to validation demands overcoming formidable obstacles. Developing new technologies and refining theoretical frameworks, this dynamic tension between skepticism and exploration exemplifies the evolving nature of scientific progress. The quest to understand black holes and their potential role as gateways to other universes remains one of the most captivating frontiers in modern physics. Although significant progress has been made in theoretical modeling and observational techniques, the ultimate resolution of this profound question lies ahead. Ongoing and future research endeavors, spanning experimental advances, theoretical breakthroughs, and interdisciplinary collaborations, promise to deepen our comprehension, or perhaps fundamentally reshape our perspective on black holes and the cosmos. One of the most anticipated avenues is the continued enhancement of observational astronomy. Building on the groundbreaking success of the Event Horizon Telescope, EHT, efforts are underway to expand the telescope array by incorporating more sites worldwide and potentially deploying instruments in space. These improvements aim to increase resolution and sensitivity, enabling dynamic, time-resolved imaging of black hole environments. Such capabilities could reveal nuanced behavior of accretion flows, magnetic fields, and relativistic jets, indirectly informing our understanding of black hole interiors and testing models, predicting exotic phenomena associated with black hole gateways. Simultaneously, the rapidly growing field of gravitational wave astronomy is poised to revolutionize our observational reach. Next-generation, ground-based observatories like the Einstein Telescope and Cosmic Explorer, with enhanced sensitivity and broader frequency coverage, will detect a larger volume of black hole mergers across cosmic time. The forthcoming space-based Observatory LISA will open a complementary low-frequency window, detecting supermassive black hole mergers and potentially signals from primordial black holes or exotic compact objects. The rich data from these instruments will be pivotal in searching for anomalies or echoes in gravitational waveform signatures that might indicate departures from classical black hole models or hint at connections to other universes. Advances in multi-messenger astrophysics, combining electromagnetic, gravitational, neutrino, and cosmic ray observations, will further enrich this exploration. Coordinated observations across these channels offer comprehensive views of black hole phenomena, improving constraints on theoretical models and unveiling subtle effects that single-mode observations might miss. This integrative approach strengthens the potential for discovering unexpected signatures relevant to black hole gateways beyond observational technology. Theoretical physics continues to push the boundaries of understanding through novel frameworks and computational tools. Efforts to develop a consistent quantum theory of gravity remain central, as resolving the information paradox, singularities, and horizon physics are crucial to clarifying whether black holes can serve as conduits to other universes. Leading candidates like string theory and loop quantum gravity offer promising, though incomplete, pictures. Advances in these fields, often spurred by insights from holography, quantum information theory, and numerical simulations, hold the key to unlocking the true nature of black holes. Computational modeling and simulations play an increasingly vital role, allowing researchers to explore scenarios inaccessible to direct experiment. High-performance computing enables detailed studies of black hole mergers, accretion dynamics, quantum gravitational effects near horizons, and potential wormhole stability. These simulations test the viability of theoretical proposals and generate predictions to guide observational campaigns. Interdisciplinary collaborations bridging physics, mathematics, and computer science foster innovation. Techniques from machine learning and artificial intelligence assist in analyzing vast, complex datasets from telescopes and detectors, identifying subtle patterns or anomalies indicative of new physics. This synergy enhances the capacity to test hypotheses about black hole gateways and related phenomena, experimental analogues of black holes in laboratory systems provide additional fertile ground. Sonic black holes, optical waveguides, and condensed matter setups recreate horizon conditions, enabling study of Hawking, radiation, and quantum effects in controlled environments. Insights gained from these analogues inform interpretations of astrophysical black holes and guide theoretical developments. Philosophical and foundational studies also contribute, clarifying conceptual issues surrounding causality, information, and the interpretation of quantum gravity proposals. This reflective work ensures coherence in the scientific narratives constructed and helps delineate the boundaries between empirical science and speculative theory. Educational and public engagement efforts play a critical role in this evolving research landscape, communicating the excitement, challenges, and implications of black hole studies inspires future generations of scientists and cultivates public support for ambitious projects. The cultural resonance of black holes as gateways stimulates dialogue at the intersection of science, philosophy, and art, enriching society's collective imagination. In conclusion, the future of research into black holes as potential gateways to other universes is vibrant and multifaceted. With advancements in observational capabilities, theoretical frameworks, computational power, and interdisciplinary collaboration, the coming decades promise significant breakthroughs. Whether these efforts ultimately confirm, refute, or transform our understanding of black holes and their cosmic roles, the journey epitomizes the spirit of human inquiry: bold, curious, and unrelenting.